Bonjour Lionel, et bien écoute, merci d'avoir accepté de faire
Ah,
un cours pour, pour cette session du master version Ecodep. Et donc je te laisse la main. Donc Lionel Truquet est professeur à l'ENSAI à Rennes et il est aussi bien sûr membre d'Ecodep. Voilà. Et il va nous raconter comment on modélise des séries temporelles en écologie. Bien.
alors, donc, ben merci. Alors, je sais pas, est-ce que je dois faire en anglais ou en français?
Écoute, au point où on en est, je pense que tu peux le faire en français. Il y a des slides qui sont plutôt en anglais, quelques
Ouais.
slides pour moi. Donc, moi, je vais arrêter ma vidéo et le son, mais évidemment, je suis là.
Bon, après, je sais pas si on le met en ligne, c'est qu'on le met. Enfin, je sais rien.
Comme tu veux, tu choisis.
Bon, allez, je vais quand même essayer de le faire en anglais. J'ai tout écrit en anglais.
D'accord, entendu.
So, so let's start this course. So, just a few words about the organization. So for this course, we will have 4 sessions, 2 in January and 2 in February. So the 2 first one will be given by me, and for the 2 last one, it will be given by Guillaume Franchi. So the 2 first session will be devoted to time series analysis for a special case of data, so-called categorical data, with some theory and method. And what I will do today is a general introduction to a field which is important for time series analysis, not only for categorical data. It's called ergodic theory. So I will make a short introduction to this topic. And what we will do during the 2 first sessions, I will first present a motivation for modeling the dynamic of absence-presence data. So this will be today on slides. Will take something like 30 minutes. And after, I will make a general introduction about ergodic theory for time series analysis, which I think is interesting for the students when you start to work on time series analysis. You cannot avoid this kind of problem, the ergodic theory and the problem of the limit theorem when you have some dependent data. The next session, I will introduce a general approach, a general theory for modeling stationary autoregressive categorical time series. So the arguments that I will use are based on my research works that I will give the reference later. And during the next session, I will also present the inference method for this kind of model. So what is the general motivation for this categorical data analysis? So first, in the field of ecology, there are many works devoted to the study of absence-presence of species in an ecosystem. And it is widely considered in the literature. And the goal of this kind of study is to explain or to forecast some binary vectors with coordinates that are equal to either 0 if there is no species at a given time, or 1 if the species is present in the ecosystem. So typically, we look at a multivariate framework. We have many species at the same time, and we want to determine and to explain why some species are present and why other species are absent when we use sensors to detect these species in some ecosystems. So the challenging problem in this field concern time series data. So in the static case, typically in ecology, they have many surveys, and on these surveys, they record if the species are present or not. And then they use some models for independent observation. So here, the challenging problem is to look at how to model the dynamic of this presence-absence data, and how to identify some interesting patterns. For instance, we want to know if the presence or absence of some species at a given time will have an impact on the absence or presence of other species in the future. And then we want also to take in account of the influence of the environment, that is of some the characteristic of the ecosystem. So what is difficult with this problem is that we have plenty models for time series analysis. Most of them are for continuous data, and for multiple binary vector, it is not very well documented. At least if we consider complex modeling, that is, we want to take in account of the time dependency, but also of some other covariates. And also more complicated, we can also use at the same time a time series model, but for which we have several time series for absence-presence data. That is a kind of spatio-temporal analysis. So this is the main motivation for this for the beginning of this course. So I will just give an example. So it's an example taken from a paper in ecology, in which they look at some surveys about the absence of presence of some water birds at different irrigation ponds. So at each pond, we record the presence of these water birds during several years. And we have many covariates at hand. For instance, we have fixed environmental and spatial covariates. For instance, the characteristic of the pond, the area, but also the presence or absence of some specific vegetation. We also have the presence of the same species that are under study at previous time. And we'll also have some indication about presence of other species than the water bird, not necessarily the bird, at time t. And the various covariates, some of them are time varying, the others are non-time varying. In this paper, many things seem to have an impact on the dynamic to explain the absence of this water bird. So the main question for time series analysis is if we want to make a model, construct a model compatible with this kind of dynamic, we want to define some autoregressive time series for binary data. And at the same time, we want to take in account of other possible covariates that are observed and which do not concern the species that we have under study. And the key point is to develop something for which we can have, of course, some probabilistic and statistical guarantee. So in this course, I will mainly work with a stationary case. So it's important to precise that for such data, we can face to non-stationarity problem. But stationarity is still a simplistic approach if we want to identify some short-term interaction between the species. Of course, if at some point after a long time period you have a kind of extinction problem, that is, you have some species that disappear, it will not be appropriate. So you can consider that it is during a reasonable period of time to identify this type of interaction. So to construct this model, in fact, it is the idea is to generalize what is done in the regression case, in the static case. So the idea comes often from econometrics in time series analysis. We can see that the categorical outcome as a discretization of a continuous regression model. That is, if yt is a random vector taking values in 0, 1 power k, we say that the species I is present at time t if a complicated function of the available covariates up to a noise term is sufficiently large or not. So you can just consider that either this functional of the covariate plus noise is positive or negative. If it is sufficiently large, say positive, we obtain 1, otherwise we obtain 0. And then here's epsilon t is a noise component. So typically, one can assume that epsilon t is independent from xt. And And the xt can contain some lag values of the response, that is the absence presence of the same species during the past. So here is a simple function, a simple link function, G, that you can use. Okay, so G is simply a vector of function with coordinate Gi, and here G is a linear function. So this is a simple model that we can take, and what is often used in the case of a regression model, it's what is called the Probit or logistic multivariate model. So at each point, I take the terminology of the example of waterbird. We look at the binary vector, and we simply take a noise, which is a multivariate probability distribution with specified margin. So the two important cases are the following, in what is used in practice. So the first one is a multivariate probit. If you look at the multivariate probit, it means that the noise term is a Gaussian vector with mean 0 and a correlation matrix R. So this is a version which is widely used in econometrics. And the second one, which is also used, is called the multivariate logistic. So here you can start with a Gaussian random vector, but we want to have marginally a logistic regression. So what we do, we take for each component the CDF of the standard Gaussian, and maybe there is a transformation that I forgot, I think. But the idea is to go back to uniform distribution, and then to take the inverse of the CDF of the logistic in order to have a logistic margin. But this one is already satisfying, and is the first one, the Probit model, is widely studied. Okay, so if I now write the model in the time series context, I will use this. So now the function depends on the past values of the response and of an additional vector of covariates. And in the linear case, you can write this with some matrices A and matrices B. So what is interesting, if you take the simple case of the linear case, sorry, there is a problem with this. It is the model interpretation, which is quite nice because you have a kind of interpretation in terms of graph. For instance, the sign, if you look at for the matrix AJ, you look at the entry I prime, it will indicate if the presence of a species I prime in the past has a positive or negative influence on the species of I, on the species I at time t. Okay, so it will have an influence if it is positive or negative, and then it have a positive or negative influence depending on the sign. The same interpretation holds for this matrix B. It will indicate if some covariates have a positive or negative impact depending on the sign of the covariates on the presence of the species at time t. When we use a multivariate Probit model, the correlation coefficients have also a nice interpretation. So typically, one can show using some classical lemma for Gaussian vector. So I will not detail this point, but when you have this kind of model, of course, the conditional correlation are not given by the correlation of the Gaussian component, but we can show that the conditional covariance between the entries of the vector YT is increasing with respect to the correlation matrix of the Gaussian noise, and they also have the same sign. So you have a kind of interpretation of association. That is, when you have a positive quantity here, in fact, the species will have, there is a tendency to have both species at the same time, and if there is a repulsive behavior, the coefficient will have a negative sign. So this is a nice interpretation for this kind of model. which make it very popular in the literature. So before starting the first part about ergodic theory, I present some references. So I have several work about some theory for including some exogenous covariates. So the first one is based on some study of what I call dependent random map. I have also a second one which studies the dependence of discrete value time series in a quite general context for multiple binary data, but also for more general categorical time series. And I have a paper that it is not finished yet, but it will be specifically devoted to this multivariate autoregressive binary model. And if you are interested in the application, mainly in the static case for this kind of multivariate Probit model, you have here the references of two papers, that one and that one, and they compare different model specification and what kind of thing we can say about the data when we apply this to some ecosystem. And the reference that I will use for today for the ergodic theory, so it is a chapter of a book from Gennady Samorodinsky. So it's not a book about ergodic theory, but there is a very nice chapter, the second chapter, which is quite concise and explain very well what are the important things from ergodic theory for the application to time series analysis. So I take this reference, but of course you have plenty of books about ergodic theory and the things that I will discuss now. So now I will change and I will go to the whiteboard, and then we will start with this first part about ergodic theory. So I hope that it works. Normally it works. Now it is stuck. I don't know why. I have a problem with the dashboard. I don't know why, because previously it was working quite well. Okay, so I think it's a problem of okay, so yeah. Okay, so I think okay, so the general framework for ergodic theory, especially the tools that I will describe now, is to get an analog of the law of large number when we have some kind of dependent data as for time series data. And this the general framework concerns what is called the dynamical system. So I will simply take a probability space with a sigma field and the measure mu. So this is a probability space. And on this probability space, so I will define a transformation which acts on the sample space F, which is a one-to-one. And measurable and such that the inverse is also measurable. That is theta minus 1. is also measurable. And we will be interested in the following situation. We say that theta preserves the measure mu. If and only if. So the push forward measure, which is written like this. So sorry, I will just delete this. Is equal to the initial measure. So for all measurable set A. So this simply says that if you look at you may view theta as a random variable, and if you look at the distribution of theta under the probability measure mu, it coincides with the initial probability measure. So this can be also written as mu of the set of X such that theta X is in A. And we say that the theta preserves the measure mu. So the fundamental example that will be important for this course is the shift operator over some sequences for the distribution of stationary processes. So I will just give the example after. So in this case, F is simply the set of sequence indexed by Z, that is the positive or negative integers, with E is simply a Borel subset of R, and theta is simply the shift operator. That is, if you take a sequence, you look at xt plus 1, for this in Z, and mu is simply the probability distribution of a stochastic process that is stationary, with X is simply xt for t in Z, stationary process taking values in E. And defined on a probability space omega fp. Say, I will A instead of F. Okay. So if you have this kind of situation, you automatically have that the shift operator preserves the measure. So the argument is the following. If you look at mu of a measurable set A, so it is simply equal to the probability that oh, sorry, this is I will directly look at the push forward measure. So this is simply the probability that X is in the set the theta minus 1 of A. which is also the probability that theta applied to x is in E. So this is also the probability that xt plus 1 for t in Z is in A. And of course, by stationarity, it is also the probability that x is in E. And this is also equal to the measure of the set A. So this is the most important example. And this is a fundamental example that we will use for time series analysis, this shift operation over the set of sequences. So when you have this kind of measure preserving probability space, we have this important result, which is a theorem which is called the Birkhoff Ergodic theorem. And we change the following. So if we take a measurable mapping from F to R, which is measurable, and such that the expectation is finite. That is, if you look at the expectation of the absolute value, which is simply the integral of f with respect to mu, is finite. So then we have the following results. If you look at the empirical average, 1 over n, the sum of t between 1 and n of f composed with theta t, that is theta iterated t times. This converges when n goes to infinity. So towards the conditional expectation, the conditional expectation of f given the sigma field capital I. So this is mu almost surely. And this capital I is simply the set of invariant subset. That's it. That is to say, the set of the events in F, which are invariant for theta, that is theta minus 1 I is equal to I. So, which this sigma field is called invariant sigma field. Okay, so I will just precise something. So this is an important theorem. It's no question to prove it because it's quite long, but it will be the basis. Okay, so if we'll just give a comment, several comments. So the first one is the following. So E is invariant, I is invariant. Then, oh, sorry. When x is in I, it means that theta x is in I. So this kind of theorem is a basis, and what we see on it is that we have a behavior which is not directly the analog of the standard law of large numbers that we have for IID observation. When we have some IID random variable, the strong law of large numbers says that at the limit you have an expectation and not a conditional expectation. So in the most general case of a dynamical system, this is not necessarily an expectation, and one can have a conditional expectation. So due to the presence of the invariant set, so here we simply look at the iteration of the transformation. You evaluate this iteration for the function f, and if we would expect a low large number, we would expect that the iteration visits quite well the support of the measure. And if it is the case, what is expected is that we have a convergence towards the mean of f with respect to the measure mu. But the main problem is that if we have an invariant set, it is not possible. So this is the second point here. So take f, an indicator function. So take 1 if x is in I and 0 otherwise. And here, if you take this kind of indicator function, when you look at the f composed with theta t, you simply obtain 1 of theta minus t of I, and due to the invariance, it is equal to 1 of I. Okay, and you can see that this empirical average is always equal to this indicator. And this indicator is different from the measure of I in general, and in general mean except if the measure is either 0 or 1. So if you have a non-trivial invariant set, that is, a measure is different from 0, 1, so you cannot obtain the expectation as you the expectation you obtain from the law large number, the usual law of large number. So the other point that I wanted to explain is the following. So if you can prove this following fact, so that a function, if you take a function f a measurable function, it will be measurable with respect to the invariant sigma field. So if and only if it is invariant under the shift. So for mu almost all x, so this is generalized the case of invariant subset. Here you have an invariant function, and okay, so I just will give a definition just after, so which motivates that when we don't have some we have some non-trivial invariant elements, we cannot have the low large number, and now we can get it if we add a constraint, which is the definition of ergodicity. So if so theta, if mu of I is in 0, 1, that is, it is either equal to 0 or 1 for any invariant subset, we say that theta is ergodic for mu. So now, if theta is ergodic for mu, one can show the following fact. The conditional expectation is measurable with respect to his invariant sigma field. And in this case, it is constant. Mu almost surely. And if it is constant, of course, it is equal to the expectation. And in this case, it coincides with the expectation. Mu almost surely. And we have the analog of the law of large number. So the other point is the translation of the Birkhoff ergodic theorem when we work with a stationary process. So if xt is stationary, if you want to express Birkhoff theorem in the initial probability space, we have the following expression, also writes as follows. It writes 1 over n sum of t between 1 and n of f of x t plus I for y in z. It will converge p almost surely toward the conditional expectation of f of x given the reciprocal image of the invariant sigma field. So that is and this new sigma field is simply defined by the set of events x in A for I in invariant sigma field. So this is a version which concerns the initial probability space on which the stochastic process is defined. In the first version of the Birkhoff theorem, it was on the image space. That is all concern the image probabilities, that is the distribution of x under P. But if you go back to the initial probability space, you can show that we have this version with the reciprocal image of the invariant sigma field. So I will give some example of now, which are interesting. So the first one is the case of IID processes. So if say so if xt or t in z are IID, I forgot the definition of ergodic process. So just after the statement of this variant of the Birkhoff theorem, the definition is the following. So we say that xt is said to be ergodic. So it's said to be ergodic. So if the probability that x is in I is either 0 or 1. So for all I in the invariant sigma field, which is simply equivalent to say that theta, that is the translation operator, is ergodic. For the push forward measure, it is the image measure, the distribution of x under the probability P. Okay, so now let us give some example of ergodic processes. And the first one concerns IID processes. That is, all the variables are independent and have the same distribution. So they are automatically ergodic. So what we will show it is possible to show this quite easily. So let an event I in the invariant sigma field, and we will show that if you look at the probability Px of theta minus n of I, and you look at the intersection of with respect to I, it goes to infinity. So it goes when n goes to infinity toward the product of the measure of theta minus n I times Px of I. That is, we will show that there is a kind of asymptotic independence when you look at these two events, the events for which you apply n times the shift. And if you have invariance, of course, this is equal to Px of I. And this, due to the invariance, will be equal to Px of I, but square. And if you have this, you can deduce that the measure is automatically either equal to 0 or 1. This implies that the probability x I is either 0 or 1. So to do this, we proceed by approximation. So let's start. So for the starting, we use a general principle in measure theory, which is the following. So I forgot maybe to precise something, is that on F, which is a set of sequence, the sigma field is simply the measure generated by what is called a cylinder set. That is the sigma field generated by some event of type so you take some coordinate, a finite number of coordinates in some Borel set C, say, and you look at this kind of events for all K, and C is a Borel subset of the Cartesian product with a 2K plus 1 element. So you look at this kind of events. So it only involves a finite number of coordinates, okay, between here time minus k to time k, and this kind of cylinder set form what is called in measure theory an algebra. And when you have a sigma field generated by an algebra, you can always approximate an element of the sigma field by an element of the algebra in the following way. So there exists, so for any epsilon positive, there exists a set E epsilon such that, so in which is a cylinder, so we just so this is called a cylinder. So we make some increments. So this is the cylinder set. So one can find a cylinder set such that the measure of the symmetric difference between I and I epsilon is smaller than epsilon, where the symmetric difference means that you simply look at what is in I and not in I epsilon. That is, you take the complement of I epsilon in I, and you take the union with all what is contained in I epsilon, and that is not in I. Okay, so in this sense, you can always approximate I by an element I epsilon of the algebra, and the algebra here is the algebra of a cylinder set. So using this kind of principle, if you look at the following properties that is written here, you can easily show that it is true for I epsilon. So let's write it. So if you look at Px of theta minus n of I epsilon, and you look at the intersection with I epsilon, it is simply the probability that some coordinates, a finite number of coordinates is in C, and the coordinates, the same set of coordinates shift n times, is also in C. And this is equal to the product by independence if n is larger than 2k, you obtain by independence the product of the probabilities. So times the probability that x n minus k n plus k is in C. And so by stationarity, it is always px of I epsilon square. So you obtain the required property that is given here for an approximation of I by a cylinder set. And now, if you can show the following. So if you want to run the proof, if it is true for I epsilon, the limit will be also true for I. You simply have to notice that if you look at px of I epsilon square minus px of I, so this is always smaller than 2 epsilon. So you simply use this fact about the approximation. So you can show that this kind of difference, so sorry, I forgot the square here, can be bounded by 2 epsilon. And you also have the following. So if you look at px of theta minus n I intersection I minus the same probability but for the set I epsilon. So uniformly on n, you can also bound by 2 epsilon. And then you can show this result. So that I will denote by a star here. And you can easily deduce star from this. Okay, so this shows that due to the independence, you always have this ergodicity property. So as a consequence, always for the example of independent observation, independent random variable, so the consequence is that you have 1 over n and the sum for t between 1 and n of f x t plus I, where I in z, it will converge P almost surely when n goes to infinity. So toward the expectation of f of x. And then you have the analog of the standard low large number. So in particular, what will be important for time series analysis in when the function f depends only on past values, that is the x before time t. This is a particular case. So this is if, of course, the expectation is finite. In particular, you can have 1 over n sum for t between 1 and n of a measurable function that only depend on past values, x t minus 1 and so on. It will go PRS with n toward the expectation of g of x0, x minus 1, and so on. Okay, this is because g is a functional that only depend on past values, and then it's a specific case of a general functional that depend on all the variables from the past and from the future. Okay, but this version is important because in time series analysis we have some observation up to time t, that is from the past and from the present. Okay, so now I will discuss a second example, which is very elementary. So this is an example you don't have ergodicity. So this is actually a very simple example. So you take simply say z plus epsilon t with z independent from epsilon. I assume that this variable is a Gaussian distribution with mean 0 and 1. And here I assume that the epsilon are IID with the expectation of epsilon 0 is finite, and the expectation is equal to 0. And now, if you look at the following set I, you take the set of sequences. So E can be equal to R here. You look at the subset such that the limit of the empirical mean, empirical average, the sum between 1 and n of xt is positive. So it is very simple to show that this is an invariant subset. Okay, because if you shift the sequence, of course, the limit will remain unchanged. It will be positive if x is already in the set I. And if you look at the probability for the distribution of x, the probability of these events, which is the probability that x is in I. So if you look at this empirical sum for x, which is a sum between z and epsilon, epsilon and IID, so the partial sum will go to 0 from the standard law of large number. And at the limit, you only obtain this variable z. And the probability to have a positive limit is simply the probability that z is positive. And since we have a Gaussian distribution, so the probability to be positive is equal to 1. Okay, so this is different from 0 and 1 or 1. And then you don't have ergodicity here. And X is not ergodic on this case. So now I will provide a characterization of non-ergodic process. I think it's insightful. If we have a stochastic process, X is not ergodic. If and only if X can be the distribution of X equals to the distribution of a mixture of two stationary processes that do not have the same distribution. So P of X is equal to the probability distribution of epsilon Y plus 1 minus epsilon Z with epsilon independent from the pair Y, Z. Epsilon is simply, it follows a Bernoulli distribution. And the distribution of Y is different from Z. So it simply says that if you don't have ergodicity, you can always represent your process as a mixture of two stationary processes. And I forgot to precise that X and Z are stationary. So it is a simple mixture between two stationary processes. So I will just give the idea for the proof, so it's not very difficult. So if you don't have ergodicity, there exists an invariant set I such that P equal to the measure of A is not in 0, 1, so it is between 0 and 1. Okay, so it's not A, it's simply I here. And what you can do is that if you look at any event I in the sigma field, so you can always write the distribution of X as P times U1 of A plus 1 minus P times another measure mu2 of A. And you have mu1 of A is simply Px so it is simply Px of A, and you look at the intersection with respect to I, and you divide by P. So this defines a probability measure, and mu2 it is the same, but you take the intersection with the complement of I. And you divide by 1 minus P. And then what you simply do is that I will not finish the proof, so it's easy to finish the proof. We show that theta is invariant for mu1 and also mu2. And then you can construct a stochastic process. So YZ. So such that the probability distribution of Y is equal to mu1 and the probability distribution of Z is equal to mu2. And of course, the distribution of these two stochastic processes will be different because they are not supported by the same set. One is supported by I and the other by the complement of I. Okay, and then after you just generate a variable epsilon, which take 1 with probability P and 0 with probability 1 minus P. And then you can see that it is possible to construct such stationary processes, such a mixture of stationary processes, which equal to for which the distribution is exactly the same as the distribution of the original stochastic process. And in the other sense, the other direction, so it is very similar. You can simply take F from F to R. So such that the expectation of F of Y is different from the expectation of F of Z. And if you look at the empirical, you have to show that it cannot be ergodic. And we simply look at the empirical mean. So automatically, so with if epsilon it is 1, you obtain the process Y here, and if epsilon is equal to 0, you obtain the process Z. But it will converge to epsilon times a random variable L1 plus 1 minus epsilon times a random variable L2. And the single solution for this to be non-random, it will be the case. It will be the case if X was ergodic. So this is random, except if L1 is equal to L2 is a constant. So is P almost surely a constant. Otherwise, you cannot obtain something which is deterministic. But this equality, this is impossible because of this difference in the expectation. If it is non-random, it is automatically the expectation for the measure Y, and here the expectation for Z. This is impossible. Okay, so this gives another way of viewing the non-ergodic behavior of the process. So now I will go back to the initial formulation with an invariant transformation on a probability space. And there is a very interesting property. When we have some what is called a compatible map, and this allows to transfer the ergodic properties to another probability space. So here I take two probability spaces. So the first one is here, and the other one is another one with the sample space G, another sigma field, and the measure on it is simply the push forward measure, which represents the probability distribution of F under the measure mu. So these are two probability spaces. And we also assume that we have theta 1 which act on F. So sorry, I will take theta act on F. I have another transformation theta bar which act on G. And both are measurable one-to-one. And also, so theta bar minus 1 are also measurable. And I suppose that F is from F to G. So it is measurable and it satisfies the following compatibility condition. If I take F composed with theta, I obtain theta bar composed with F. So if theta preserves mu, then theta bar will preserve the push forward measure. And if we have ergodicity for theta, it implies that theta bar is also ergodic for the image measure or the push forward measure. So this is the whole proposition. So it's a way of transferring ergodicity. So it is very simple to prove. So if you want to prove this, to show that theta bar preserves the push forward measure, we simply note that if you look at the push forward measure, so taken at theta bar minus 1 of A, so it is simply mu of f minus 1 of theta minus 1 of A, but it is also mu. So, okay, I have theta bar. So it is also mu of theta bar composed of f minus 1 of A. But if you use the compatibility condition, this is equal to this kind of thing. So this is because of this compatibility property. And then this is simply mu of theta minus 1 of f minus 1 of A. And this equal, due to that theta preserve mu, it is simply the measure of f minus 1 of A, which is simply the push forward measure of the set A. So in this case, we see that automatically theta bar preserves the measure, the push forward measure. And for the ergodicity, it's similar. So we have an invariant subset for theta bar, which means that J is invariant for theta bar. We simply we set I. So we want to show that the push forward measure of this J is equal to 0 or 1. So we simply take the reciprocal image of J. And what we simply have to notice is that I is an invariant subset for theta. That is theta minus 1 of A is simply theta minus 1 of f minus 1 of J, which is simply f composed with theta minus 1 of J. And due to the compatibility condition, this is theta bar composed with f minus 1 of J. And this is simply, it is exactly the same argument as before. So you obtain f minus 1 of theta bar minus 1 of J. And due to the invariance, it is simply f minus 1 of J, and it is simply I. So if I is invariant for theta, and theta is ergodic for mu, so if mu of so if theta is ergodic for mu, so if mu, sorry, so automatically mu of I is either 0 or 1. Then, so the push forward measure of J is also either equal to 0 or 1, which shows that we have ergodicity for the image measure. And then this ends the proof. So I will give some example of this, which are quite interesting, I think. So it's the example of a transformation that is always used in time series analysis for showing ergodicity of something which is more complex. When we have this kind of space of sequences indexed by Z. So we take another space of sequences indexed by Z, and you still take this theta bar. So we change the shift operator on F and G. And you take the following function, F of X is simply defined by a mapping H of the iteration of theta evaluated at X for T in Z, with H is a measurable mapping from F to E bar. And if you look at this kind of situation, when you take the composition between theta bar and F of X, so you simply shift this expression. So you obtain A of theta T plus 1 of X. And this is simply the composition of F and theta of X. Okay, so here you simply shift this quantity, and here you start to shift this quantity, but it is exactly the same result. So you have the compatibility condition, and the important consequence is the following. So if you take an ergodic process, so if xt is ergodic, then if you look at this transformation yt, which is simply h of x t plus I over I, then this yt is also ergodic. Okay, so it means that when you take an ergodic process, if you take this transformation of this ergodic process of this form, you still obtain an ergodic process. And what is important in time series analysis, it's the case where yt is a function h, say tilde, it's not the same than h, so which depend only on the past values of an ergodic process. And so on. So this is a specific case of a process which depend on all the variables. So here it only depends through the function h tilde of the past values. And it is interesting in time series analysis because we know that every time we have an ergodic process, if you take a functional of past values of this ergodic process, we still obtain an ergodic process. So this is a consequence of the proposition. So this is the first example. So I will show the second one. So the second one concerns the time reversal. So what we do, we set f of x is equal to x minus t. So with f over e power z toward e power z. So maybe it's not very well written here. It's really minus x minus t. So this is time reversing. And if you look at this time reversing, so you define theta bar is simply the inverse of theta. And if you look at theta bar and you compose with f of x, so this gives the sequence x minus t plus 1 for t in z. And this is also the same thing as if you compose f with theta. And the consequence is that when you look at a stochastic process, if you look at xt ergodic, it implies that you still have ergodicity if you take a time reversal. Okay, so so the following consequence of this ergodicity property, I will just mention a kind of summary. So if x is ergodic, so if you look at the partial sum, so you take this kind of empirical average of f of x d plus I. So you take a function that depends on all the coordinates. So it will go through, it will converge towards the expectation. So when n goes to infinity, p as p almost surely. So if we have integrability, in particular, every time you have something which only depends on the past, it is a specific case. So if I only take xt minus 1, I only take the past direction, which is fundamental for time series. So you can show that you have a convergence toward this quantity. And also, if you think that when you reverse the time, you still keep the ergodic property, you have this situation. You can show that when you take fx minus t, x minus t minus 1, and so on, you take only past values. This also converges to the same expectation. Okay, so so that one is a general convergence. This one is the convergence which is the most useful in time series analysis, because typically we look at the law of large number for some functional of past or present variable indexed by the time t and at previous time. And that one will be also necessary in one proof that I will give for the construction of categorical time series. But you have both. You have the three type of convergence for the three type of situation here. So this is obtained after time reversing. Okay, so now I will also mention another notion, and I think that Paul already introduced this notion in his previous course. It's the notion of alpha mixing.
Absolument.
And this is a kind of notion which relaxes the independence notion, which is very useful in time series analysis, and which is in particular useful for non-parametric estimation in statistics. So we say that X so stationary is alpha mixing if the following coefficients, which is simply you look at the largest value that you obtain when you look at the probability of the intersection of two events. The first one concerns path value of the sequence, so say before 0, in a measurable set A, and the other is simply the value that you obtain in the future after time n, and you compare the probability of the intersection minus the product of the probabilities, which will be the probability of the intersection if the past and the future were independent. And it is mixing if this kind of quantity goes to 0. So if you prefer, it's a kind of asymptotic independence notion. So we look at what happens for the process before time 0, and you look at an event which concerns the process involving the variable after time n, starting at n, and you look at the difference between the probability of the intersection and the product of the probability. If the past and the future were independent, we will obtain 0. So when we have dependence, it's not necessarily the case, but we want to see how far are this the probability of the intersection and the product of the probability uniformly with respect to all the possible measurable sets. And when the distance between the past and the future goes to infinity, when n goes to infinity, we say that we have alpha mixing if this coefficient goes to 0. So here it's a formulation for stationary process, but we can compare some past value before, not time 0, but time k, and in the future, starting from n plus k. So due to stationarity, it's not important. So this is why we only define the past as the variable before time 0, but it has no importance due to stationarity. So I think that Paul introduced this in the last course, and the main point is that this property is in fact stronger than ergodicity, but is more useful in some situations for which ergodicity is not sufficient for studying consistency of parameters. alpha mixing imply ergodicity. So it's quite easy to prove this. Once again, by approximation. So I take an invariant set, I, in the field of invariant subset, which means that theta minus 1 of I is equal to I. So once again, I will approximate this event I by an event only involving a finite number of coordinates. This is exactly the same argument as for proving that independent processes were ergodic. So I consider I epsilon. It is simply the set of sequence such that x minus k up to the coordinate xk is in the measurable set C, and such that the probability of the symmetric difference is controlled by epsilon. And once again, it's quite easy to prove the following. If you look at the probability of the intersection between theta minus n I epsilon, and you take the intersection with I epsilon. As for the case of some processes with independent coordinates, so this is still written, the probability is that x minus k up to xk is in C. And if you shift the coordinate, x n minus k up to x n plus k is in C. Since we have stationarity, k can be equal to 0. Okay, here it is exactly the same probability, but if you use the fact that it is alpha mixing, when n goes to infinity, so it will converge toward the following probability. And you take, of course, the square. And this is because when n goes to infinity, the probability of the intersection will converge towards the product of the probability. And this is because we have an alpha mixing property. And we can also show that this is exactly the same argument you can approximate by this cylinder set. The probability of the intersection of theta minus ni and I converge toward px of theta minus I times the probability of I when n goes to infinity. So this can be done because you have this property for I epsilon, and uniformly in n, you can approximate. So sorry, so this is a problem here. This is not totally correct. It is just because I take the difference here. And I should simply say that if I take the absolute value of the difference, it goes to 0 when n goes to infinity. So this is because each probability here, the intersection and the product, can be uniformly approximated by the corresponding probability for I epsilon, so uniformly in n, due to this property about the symmetric difference. And the argument is the same. And here you can just remind that this quantity is equal to px of I, and this quantity here is given by px of I square. Okay, and then you can simply say that px I is in 0, 1, which implies that x is ergodic. So this ergodic notion holds for independent observation, but also for independent observations that are asymptotically independent, such that the processes that satisfy the alpha mixing property. But sometimes ergodicity is still sufficient for time series analysis, as long as a version of the law of large number is sufficient for studying consistency of the estimators. But sometimes ergodicity is not sufficient, especially, for instance, in non-parametric estimation. And we have to use this stronger notion, which was introduced by Paul last time, and which is called alpha mixing. So this is one possibility of weakening independence. And I will also discuss these alpha mixing properties for categorical time series, as well as the weaker condition, which is ergodicity. Okay, so this ends the first part about the basic things in ergodic theory. So I don't know if some people have questions. I don't know who is connected or not now.
In fact, there are quite a lot of students, because there is a group of students.
There is a group of students. So
there was, in fact, there are people which connect and disconnect.
Okay. So for the students in the Master of Sergi, what I propose is to detail a bit more the proof that I give here, because here it's quite clear for this kind of independence. But here, what is not very well detailed is the approximation. I say that I have this, and then I can show this. So I propose for you to, if you take the proof, to finish to detail a bit more the proof. And there is also, for instance, this kind of example that I show here. That is when we have a non-ergodic behavior. So it was here. Sorry, it was here. When we have a non-ergodic behavior, necessarily it's equivalent to we have necessarily a mixture of stationary processes with a different distribution. So I gave some arguments here, but maybe it's quite fast and you need more details. So I propose that you detail a bit more this proof, and you carefully write all the details, because I skipped many details here. For the moment, I think it's okay. And I think that okay, so it's okay for the moment. What I wanted to do. So here it's the same. Here there was a mistake. I realize this. So it's not totally correct in the sense that what we simply want is that we want to show that
the slides will be online soon also.
This simply says that it is equivalent in the sense that the difference will go to 0 when n goes to infinity. Okay. So if you take the difference, it is exactly as for mixing processes, you take the difference and it goes to 0. But you can simply say it is more correct to say this, for instance. So I will simply write the correct things that so this go towards this when n goes to infinity, because there was a n in the limit and it was not correct. And here something missing. Okay. So I will stop to share my screen. So what I think is that for today it will be sufficient. I don't know, because next time I will use this basic notion to define a theory for categorical time series, and I will study also the dependence properties. So maybe we should stop now.
Sure. Okay, so I will stop the.
If you don't have a question, because we can discuss.
I will stop the record, and if you want, you can just go on a bit. Okay.